In this problem, we're going to find V0 using Thevenin'S theorem. Again, we're going to use a problem-solving strategy entitled Applying Thevenin'S theorem. And if you remember, the first step there is we remove the load and find the open circuit voltage. So let's identify our 1K as the load, because that's the element that V0 is across. So we're going to remove this element. We'll make terminals A and B. We're going to calculate the Thevenin equivalent. So we're going to calculate this circuit, open circuit voltage, Thevenin resistance. Then we're going to hook up the 1K resistor to the Thevenin equivalent and calculate V0. So we're going to remove the 1K, calculate V open circuit. Now, since we have dependent sources and independent sources, if you look at step 2C of our problem solving strategy, we're going to also have to find the short circuit current. So this problem is going to require us to find the open circuit voltage and the short circuit current. So here's our circuit that we're going to use to calculate the open circuit voltage with. And if we look and say, what technique should I use? Let's look at the circuit. For instance, if we apply Kirchhoff's current law here, we see that Ix prime is 2 milliamps. That means this voltage source has a value of 8 volts. So that voltage is known. So if we were to look, we could do mesh or nodal, either one. And what I'm going to do is, let's do this one with nodal. So let's pick this node as a reference, and we'll assign 2 node voltages, V1 and V2. And also we'll have a supernode, and we'll have a constraint equation. So our constraint equation is V1 minus V2 equal to 8. Then if we apply KCL to the supernode, we'll have this current, we'll have V1 over 3K. This current will be V2 over 6K. We'll have 2 milliamps entering, so that'll be minus 2 milliamps. We'll have 2 milliamps leaving, so that'll be plus 2 milliamps. Then we'll have 8 milliamps entering, so we'll have minus 8. So here we get 1 over 3K times V1 plus 1 over 6K times V2 is equal to 8 milliamps. And there's our second equation. If you go through and solve, you'll get V2 is 32 over 3 volts. And now, we need to calculate V open circuit. And to do that, we'll do KVL around this loop. We know that the voltage across this resistor is 4 volts because we know the current flowing through it. So VOC is 4 plus V2. So around this loop we have 4 plus V2, and this turns out to give us 14.67 volts. So that completes our calculation of the open circuit voltage. Now we need to calculate the short circuit current. Here is the circuit for calculating our short circuit. And again, I'm going to use nodal analysis. We'll pick this one as a reference. I'm going to call this node voltage V3. I'm going to call this one V4. Again, we have a supernode. So we'll have a constraint equation. And if I had used mesh here, I got 4 meshes, I'd have 2 known ones and 2 unknown ones. So here I decided to go with nodal. Again, we only have 2 nodes. We have a constraint equation. That constraint equation is V3 minus V4 is 4K IX double prime. Now if I look at the circuit, and if I think about the current flowing in this direction, let's call it IA. IA is V4 over 2K. Notice that IA is defined in the opposite direction of IX double prime. So IX double prime is minus V4 over 2K. So if we substitute this in, we'd have V3 minus V4 equal to 4K times minus V4 over 2K. And we cancel and get a 2. What we get out of this is that V3 is equal to minus V4. So our constraint equation tells us V3 is equal to minus V4. Now, if we apply KCL to the supernode, we'll have V3 over 3K, be that first term. This one will be V4 over 6K. Then we'll have V4 over 2K, which is this current IA. That's equal to, we have a current of 8 milliamps entering from sources and 2 milliamps leaving from that current source. Okay, so if we look at the arithmetic, if we substitute in here minus V4, we have a 6 plus a half, which is 2/3. We have minus a third, so basically we have 1/3 V4 is equal to 6 milliamps. So it turns out V4 is equal to 18 volts. So that's just plugging this into this equation. Now, how are we going to calculate I short circuit? Well, we'll apply Kirchhoff's current law at that node. So, I short circuit then is V4 over 2K plus 2 milliamps. Well, V4 is equal to 18. If we substitute that in, we get 9 milliamps plus 2 milliamps, which says that I short circuit is 11 milliamps. So now we've calculated both V open circuit and I short circuit. So now we can calculate our Thevenin. Our Thevenin is the ratio of V open circuit to I short circuit. So we have 14.667 divided by 11 milliamps, and that gives us 1.33 kiloohms. Okay, so here's our open circuit voltage and Thevenin resistance. Here's our terminals A and B. We hook up the 1K resistor to calculate V0. So we get V0 by voltage division. And it turns out to be 6.2858 volts.